Okay, today we're going to discuss about sampling, and let's assume that we have a continuous signal x of t, and let's assume that we are gonna sample it every ts seconds, for example. And in order to do that, we need to consider the Dirac train Pt given by the sum minus infinity to infinity of deltas, and 0 ts to s and ts. So here we have how the Dirac train, also minus ts, and in order to obtain the discrete sample signal, what do? We take x of t and we multiply it by the Dirac train, and the output is going to be a sample signal, which I'm going to call the Diractified signal. Why? Because x of s of t, x sub s of t, is equal to the original, the continuous signal multiplied by pt, but this is equal to what? This is equal to x of t, which multiply the infinite sum of this bunch of deltas, and this we can take advantage of. The multiplication is linear, is a linear operator, so this is equal to the sum over n from minus infinity to infinity of x of t times delta t minus nts. And by applying the localization property of the delta, this is equal to the sum of x applied at nts times t minus nts. So let me write it in a better form here. X nts times delta t minus nts. So what's going to happen that this signal is a diractified signal because it contains the discrete values of the continuous function at each time nts are basically stored as the strength of a delta Dirac, and that's how the signal look like. Now, what I would like to show is, let's assume that now, given this diractified signal, we would like to apply a filter to this signal and reobtain the original signal, the continuous one, or at least understand what are the conditions under which we can recover the original continuous signal. So now we would like to take this, rectify the signal, put it inside a filter that we need to design, and see if we can recover the original continuous signal. But we need to do the design of this filter. Design filter. And also understand, what are the conditions under which the full recovery of the signal can be obtained. So that's basically the main the big picture of about sampling. So you start with a continuous signal. You sample it by multiplying with a Dirac train. The output is a Diractified signal. Diractified signal. And now what we would like to do is to take this signal, pass it through a filter that we need to design, and see if we can regain the original continuous signal. So the question is, what is this filter? We need to design it. Let's see how to do that. Now, in order to do that, every time we want to design a filter, we need to. It is better to do it in the Fourier domain, and for this, we need the spectrum of the Diractified signal. Because once we have the spectrum of the Diractified signal, we can understand how to filter it and see if we can recover the original signal. So we need to work in the Fourier domain. And now, of course, the Dirac train is this. And we already I've seen what is the Fourier transform of this of the Dirac train. We're gonna revise it again today, and now we already know that x of t is given, and so we can immediately compute this Fourier transform. So we have a continuous signal in time. And we're going to assume that the Fourier transform is this is just a characteristic shape to denote the spectrum x of omega. And we're going to assume that let's assume that the spectrum is bounded, is defined on a compact support, bounded by minus omega b and omega b. So it's going to be 0 outside of this range. Now regarding and this is regarding the spectrum of the x of omega, the spectrum of the continuous signal x of t. This is given. Regarding the Fourier, the Dirac train, so we know that in the time domain, the Dirac train is a periodic function of time with period Ts. And the correspondent Fourier transform can be derived in different forms. If you're going to do we can do the direct approach and basically do the Fourier transform of the sum over n of delta t minus n ts. but this is equal to the sum over n from minus infinity to infinity of the Fourier transform of delta t minus nts. But now here we can apply the time shift property of the Fourier transform. So we're going to get e to the minus j omega nts times the Fourier transform of delta t, which is basically 1. So this is the Fourier of delta t, which is equal to 1. And this term comes from the time shift property of the Fourier transform. So, and here now we get a first form of the Fourier transform of the Dirac train, which is given by this infinite sum that could be helpful. We're going to see how we can use it. But of course, we can also exploit the fact that the original signal is a periodic function of time. So we can derive the Fourier series of P of t, and then we do the Fourier transform of the Fourier series. And we're going to get an alternative expression of this guy. So let's see how to do that. And so we have P of t is given by the sum from n equal minus infinity to infinity delta t minus nts. And if we do the brutal approach by taking the Fourier transform of this sum, this infinite sum, we're going to get P of omega equal sum from n equal minus infinity to infinity of e to the minus j omega nts. Alternatively, what we can do, evaluate Fourier series of, okay, and then take the Fourier transform. This is indeed a periodic function of time. Let's assume that these are 0, ts, 2ts, minus ts, minus 2ts. So we're going to take this interval, which is ts over 2 and minus ts over 2. And I can write P of t as the sum from k equal minus infinity to infinity of a of k e to the j 2 pi over t sub s, because now the period of this periodic function is ts. T sub s is the sampling time. Kt. And we know that the Fourier coefficient a of k are given by 1 over ts integral between minus ts divided by 2 and ts divided by 2 of P of t e to the minus j 2 pi ts kt in delta t. But now we know that within this interval, this is equal to delta t. And so when we do this integration, we simply integration of a delta with another function, which is a nice function. It will sample the value of this function at t equals 0, which is going to be equal to 1. So the final result is going to be 1 over ts. So the Fourier series of pt is given by the infinite sum of 1 over ts e to the j 2 pi ts kt. And we are done with this part. So now I can take the Fourier transform of this infinite series, and the Fourier transform is given by so P of omega is going to be equal to what? To the Fourier transform of this infinite sum. Because of the linearity of the Fourier transform, I can swap the sum with the operator, the Fourier operator, and here I have minus infinity to infinity of 1 over Ts, the Fourier transform of e to the j 2 pi Ts kt. But now here I can apply the modulation properties of the Fourier transform, because here I can assume that this is 1 times 1, okay? So this is equal to the sum from k equal minus infinity to infinity of 1 over Ts, the Fourier transform of 1, which is basically 2 pi delta of omega, but shifted by this frequency omega sub s times k. So minus k 2 pi Ts. And so we got an alternative form of the Fourier transform of the Dirac train. So we have this infinite series given in this form, but also we get this infinite series. This is an infinite series of exponentials, and here we have an infinite series of deltas. And so, the two Fourier transforms are equivalent. Okay, so here now I'm calling this ratio 2 pi over Ts, the sampling frequency. So omega s equal 2 pi over Ts, and this is the sampling frequency. So let's summarize what we have done so far. So I'm gonna keep these results here. Actually, let me redo it again.